Picture this: a beam of sunlight traveling 93 million miles through the void of space, finally piercing Earth's atmosphere after an 8-minute journey. It's something we take for granted every single day, but light is so much more than just what lets us see the world around us. It's the universe's oldest messenger, carrying secrets across time and space, from the birth of stars to the edges of black holes. And here's the wildest part: scientists still argue over what light actually is. Is it a wave rippling through space like water in a pond? Or is it a stream of tiny particles flickering in and out of existence? The truth, it's both and neither. Light defies our everyday logic, and that's what makes it one of the most fascinating puzzles in all of science. Think about it: every color you've ever seen, every sunset that took your breath away, every twinkle from a distant star, all of it comes down to this enigmatic phenomenon. Ancient philosophers believed light was a kind of fire emitted by the eyes. Centuries later, Newton thought it was made of tiny corpuscles. Then came Einstein, who showed us light behaves like a particle and a wave, depending on how you look at it. And today, we're using light to probe the deepest mysteries of the cosmos, from the quantum realm to galaxies billions of light years away. It's the thread connecting everything: our reality, the atoms in our bodies, even the fabric of space-time itself. So buckle up, because we're about to embark on a journey through the true nature of light, from the first flickers of human curiosity to the mind-bending experiments reshaping physics as we know it. We'll uncover how light bends around stars, how it powers quantum computers, and why it might hold the key to understanding the universe's greatest secrets. By the end of this, you'll never look at a sunbeam or a neon sign the same way again, because light isn't just something we see, it's the very language the cosmos uses to reveal itself. And trust me, the story it's telling is more incredible than anything we could have imagined. Long before we had lasers or quantum theories, Galileo Galilei was climbing towers in Italy with nothing but a lantern and a burning curiosity. He'd flash the light at distant observers, timing how long it took for them to signal back, crude by today's standards, but revolutionary for the 1600s. This was one of the first attempts to measure light speed, and though his results were wildly off, it marked a turning point. No longer was light just a mystical force. It became something to dissect, measure, and understand. Fast forward a few decades, and two giants of science, Isaac Newton and Christian Huygens, were locked in a fierce debate. Newton insisted light was made of tiny, fast-moving particles he called corpuscles, like microscopic bullets shooting through space. It explained why light traveled in straight lines and cast sharp shadows, but Huygens fired back with his wave theory, arguing light rippled through an invisible medium called the ether, like sound through air. For over a century, these ideas clashed, with no clear winner. Then came Thomas Young's legendary double-slit experiment in 1801. He shone light through two narrow slits onto a screen, expecting simple bands of brightness. Instead, he saw something astonishing: alternating light and dark stripes, a pattern only waves could create. It was as if two stones dropped in a pond. Their ripples overlapped, some peaks amplifying each other, others canceling out. Light wasn't just a wave, it interfered like one. This shattered Newton's particle model and seemed to crown Huygens the victor until the 20th century flipped the script again. Because here's the twist: light refuses to play by just one set of rules. When Einstein studied the photoelectric effect, he found light knocking electrons loose like discrete particles, not waves. So which is it? The answer, as quantum mechanics revealed, is both. Light dances between particle and wave, changing its nature depending on how we observe it. It's as if the universe itself is whispering, "Why choose?" This duality became the cornerstone of modern physics, proving reality is far stranger than Galileo, Newton, or Huygens ever dreamed. And the deeper we dig, the more light reveals not just about itself, but about the very fabric of existence. Einstein's breakthrough came not from staring at the stars, but from studying something far more ordinary, a piece of metal. In 1905, while working as a patent clerk, he tackled a puzzle that had stumped scientists for years. Why did certain metals eject electrons only when hit by specific colors of light? Classical physics insisted light was purely a wave, so brighter light should always knock electrons loose. But experiments showed something bizarre. Blue light, even if dim, could trigger the effect, while red light, no matter how intense, failed. It made no sense until Einstein dared to rewrite the rules. He proposed light wasn't just a smooth wave, but a shower of tiny energy packets he called quanta, later known as photons. Each photon carried a fixed amount of energy tied to its color, like discrete droplets in a downpour. Blue photons packed enough punch to dislodge electrons. Red ones, with their lower energy, simply couldn't. This explained the mystery perfectly, but it also shattered the elegant wave theory of James Clerk Maxwell, which had ruled physics for decades. Scientists recoiled. Even Max Planck, whose work inspired Einstein, called the idea a step backward. The irony: Einstein's photons were the first crack in the dam of quantum theory, a flood he'd spend the rest of his life trying to contain. He accepted light's particle nature when it solved his problem, but recoiled when others extended quantum weirdness to reality itself. God does not play dice, he famously protested, while his own work proved the universe was far stranger than dice rolls. Yet this tension between wave and particle, certainty and probability, became the engine of modern physics. Today, we know light is neither just a wave nor just a particle, but something beyond both, a quantum entity that morphs based on how we interrogate it. Shine it through slits, waves, aim it at a solar panel, particles. This duality isn't a flaw, it's a feature woven into the fabric of reality. And every laser, every LED, every fiber optic cable in your life exists because Einstein dared to ask, what if light keeps secrets? Imagine standing in Copenhagen in 1676, staring at a telescope pointed at Jupiter. Danish astronomer Ole Rømer noticed something peculiar: the planet's moons didn't eclipse on schedule. When Earth moved farther from Jupiter, the eclipses lagged. When closer, they arrived early. His groundbreaking realization: light wasn't instantaneous, it took time to travel. By tracking these delays across Earth's orbit, Rømer calculated light's speed for the first time in history: 220,000 kilometers per second. Not perfect by today's standards, but a revelation that shattered centuries of assumption. Fast forward to today, and we've refined that number to an almost unimaginable precision: 299,792 kilometers per second. Not a single digit more or less. This isn't just a speed, it's the universe's ultimate speed limit, woven into the fabric of spacetime itself. Einstein's theory of relativity hinges on this cosmic rule: nothing with mass can ever reach it, and no information can travel faster. But here's where things get surreal. If you could ride a light beam like a surfer on a wave, time would stop for you entirely. Clocks on Earth would tick infinitely fast in comparison, while distances ahead would shrink to nothing. Light doesn't just move, it warps reality around it. This leads to one of Einstein's most famous thought experiments. Picture chasing a beam of light. If you matched its speed, the wave should appear frozen, like a static ripple in a pond. But Maxwell's equations, the bedrock of electromagnetism, insist light must oscillate. The paradox forced Einstein to rewrite physics, proving time and space aren't fixed but stretch and compress to keep light speed constant for all observers. And here's the cosmic bonus: light speed is also a time machine. When we gaze at the Andromeda Galaxy, we're seeing it as it looked 2.5 million years ago, its light only now reaching us. Every sunrise is an 8-minute-old snapshot of the sun. Even your reflection in the mirror is nanoseconds behind, a tiny echo of the past. Light doesn't just connect us to the universe, it archives it, offering a window into epochs long gone. So next time you flick on a lamp, remember, you're not just illuminating a room, you're touching the same phenomenon that carries whispers from the dawn of time. Every time you look up at the night sky, you're not just seeing stars, you're staring into a cosmic scrapbook, pages filled with light that took centuries or even millennia to reach your eyes. Take the Orion Nebula, for example, that glowing stellar nursery. Its light left there around 1300 years ago, back when humans were building the first Viking longships. And the Andromeda Galaxy, you're seeing it as it was when early hominids walked the Earth. Telescopes aren't just tools, they're time machines, collecting ancient photons like postcards from the past. But here's where it gets wild. While our eyes are stuck viewing a delayed universe, neutrino detectors tell a different story. These underground labs catch particles from the sun's core, but unlike sunlight, which takes 100,000 years to fight its way through the sun's dense interior, neutrinos zip straight to Earth in just 8 minutes. It's like having two windows into the same star, one showing a live broadcast, the other a rerun from the Bronze Age. This creates a bizarre paradox. Are we really seeing the universe as it is, or just a patchwork of outdated signals? That's where Redshift comes in, light's own built-in time stamp. When distant galaxies race away from us, their light stretches like a cosmic yawn, shifting toward the red end of the spectrum. Edwin Hubble first noticed this in the 1920s, realizing the farther a galaxy was, the faster it seemed to flee. This wasn't just motion, it was space itself expanding, carrying galaxies along like raisins in rising bread dough. Today, Redshift reveals something even stranger. The universe isn't just expanding, it's accelerating, pushed by some mysterious force we call dark energy. Yet light gives us more than just cosmic speedometers, it's nature's ultimate barcode scanner. Pass starlight through a prism, and dark lines appear at specific wavelengths, each a fingerprint of elements in that star's atmosphere. Sodium absorbs here, iron there, oxygen somewhere else. It's how we know the sun contains helium, named after Helios, the Greek sun god, before we'd even found it on Earth. Modern telescopes use this trick to map galactic chemistry millions of light years away, finding water on exoplanets and even detecting organic molecules in interstellar clouds. So next time you turn on a lamp, remember that humble glow connects you to techniques that decode stars, measure the universe's expansion, and maybe, just maybe, hold clues to the greatest mystery of all: why everything exists at all. Think of the electromagnetic spectrum as a grand piano stretching across the cosmos with the keys representing every possible wavelength of light. Our eyes can only detect one tiny octave in the middle of visible light, that narrow rainbow from violet to red. But just as a piano holds symphonies beyond a single scale, the spectrum hums with invisible wonders. To the left of our familiar colors, radio waves ripple with wavelengths longer than skyscrapers, carrying whispers from the birth of the universe. To the right, gamma rays pack energies so fierce, a single photon can outshine the sun. Take radio waves, the gentle giants of the spectrum. Their sprawling wavelengths mean they can glide through dust clouds and atmospheres untouched, like low notes resonating through walls. Radio telescopes collect these cosmic murmurs, revealing hydrogen clouds where stars are born, or tracing the faint afterglow of the Big Bang itself. Then there's microwaves, not just for reheating leftovers. The same waves that warm your coffee also map the universe's baby pictures, the cosmic microwave background, a snapshot from when the cosmos was just 380,000 years old. Shift higher and infrared light paints the warmth of the universe. Ever seen a heat signature? That's infrared revealing what eyes can't. Dust glowing around newborn stars or hidden galaxies veiled behind cosmic curtains. Even your own body radiates it, a reminder that we're all part of this light-drenched universe. Now cross into the realm of X-rays, where light becomes a cosmic surgeon's knife. These high-energy photons slice through soft tissue but collide with dense bone, or in space, they ricochet off the million-degree plasma around black holes. Chandra Observatory uses this superpower to expose the violent hearts of galaxies, where gravity twists spacetime into knots, and at the spectrum's far edge, gamma rays blast from the universe's most cataclysmic events, colliding neutron stars, supernova, or jets screaming from quasars. A single gamma ray burst can outshine an entire galaxy for seconds, a flashbulb illuminating the darkest corners of spacetime. Here's the cosmic joke: nearly all of this symphony is silent to our biology. We evolved to see the one sliver of light that penetrates Earth's atmosphere and reflects off leaves and water, a survival tool, not a universal truth. But technology lets us eavesdrop on the full concert. Night vision goggles amplify infrared. Airport scanners borrow X-ray vision. Your phone's GPS syncs with satellites using microwave chatter. Even Wi-Fi rides radio waves, turning your living room into a node in this grand electromagnetic dance. So next time you scroll on your phone or warm soup in the microwave, remember, you're harnessing the same invisible forces that unveil black holes, map galaxies, and echo the universe's first breath. The spectrum isn't just out there, it's woven into every flicker of modern life, a bridge between the cosmic and the everyday. Centuries before compasses lit up dashboards, Viking sailors were navigating stormy North Atlantic waters with nothing but a chunk of crystal. On overcast days when the sun vanished behind thick clouds, they'd pull out their sunstones, calcite crystals that revealed the sun's position through polarized light. By rotating the stone until its brightness aligned, they could pinpoint the hidden sun like a cosmic compass needle. This wasn't magic, it was an ingenious hack of one of light's most overlooked properties, polarization. Here's how it works. Ordinary light vibrates in all directions like a tangled jump rope. But when reflected off water or scattered through the atmosphere, those vibrations get combed into alignment, like the rope now snapping straight up and down. Polarizing filters act as microscopic picket fences, only letting through waves vibrating in one direction. That's why polarized sunglasses cut glare from wet roads. They block horizontally scattered light that overwhelms our eyes. But the Vikings weren't just reducing glare, they were decoding celestial GPS signals hidden in plain sight. This same principle now helps astronomers map magnetic fields across galaxies. Starlight gets polarized as it squeezes between interstellar dust grains aligned by magnetic forces. Like cosmic breadcrumbs, these twisted light waves trace invisible magnetic skeletons shaping star nurseries and black hole jets. The Hubble Space Telescope even found polarized light swirling around distant exoplanets, hinting at atmospheric winds faster than hurricanes. Your everyday tech owes its existence to this hidden quality of light. LCD screens are stacked polarizers. Electric currents twist liquid crystals to block or pass light, painting each pixel on your phone. 3D movies work by feeding each eye differently polarized images. Even honeybees see polarized patterns in the sky, using them as a navigation grid humans can't perceive. but the real cosmic head-scratcher. The universe itself glows with faint polarized light from the Big Bang's afterglow. This primordial fingerprint, called B-mode polarization, might carry imprints of gravitational waves from the universe's first trillionth of a second, a smoking gun for quantum fluctuations that birthed all galaxies. Some theories suggest dark matter particles could subtly tweak this polarization, leaving ghostly signatures we're just learning to read. So next time you adjust your sunglasses or tap a smartphone screen, remember, you're touching the same phenomenon that guided longships through fog and now helps physicists hunt for the universe's missing 85%. Polarization isn't just a neat optical trick. It's a secret language light uses to whisper about magnetic storms between stars, the birth cries of the cosmos, and shadows of invisible matter bending reality itself. Let's return to that iconic double-slit experiment, but this time with a twist. Imagine firing single photons one at a time through the slits. Common sense says each photon should pass through one slit or the other, creating two bright spots on the screen. But quantum mechanics laughs at common sense. Even when photons travel solo, they still create an interference pattern, as if each particle splits into a ghostly wave, passes through both slits simultaneously, and interferes with itself. It's not just light behaving as both particle and wave, it's light refusing to choose until forced. This brings us to the observer effect, one of quantum mechanics' most mind-bending revelations. The moment you place a detector to see which slit the photon takes, the interference pattern vanishes. The photon stops acting like a wave and picks a single path, as if the act of measurement forces it to make up its mind. It's not that the detector disrupts the photon, it's that the photon exists in a blur of possibilities until observed, a concept so unsettling even Einstein struggled with it. Richard Feynman took this further with his sum-over-paths approach, suggesting light doesn't just take one path or even two, but every possible route between points, including looping around the moon or zigzagging through your coffee cup. These paths cancel out in most cases, leaving the familiar straight-line trajectory we see. But in quantum realms, light's true nature is this infinite exploration of all options, a cosmic game of try everything and keep what works. Now contrast this with Niels Bohr's complementarity principle. Light isn't secretly both wave and particle, it's neither, revealing one face or the other based on how we interrogate it. Like asking if a spinning coin is heads or tails mid-flip, the question itself changes the answer. This isn't just philosophy, it's the foundation of quantum technologies today. Which brings us to entanglement, where pairs of photons become mysteriously linked, instantly mirroring each other's states no matter how far apart. Measure one's polarization here, and its twin snaps into a correlated state light years away, defying locality. Einstein called it spooky action at a distance, but it's very real, and it's the backbone of emerging quantum encryption. Imagine sending a message encoded in entangled photons. Any eavesdropper's measurement would collapse the quantum state, alerting you instantly. From ghostly waves to spooky connections, light's quantum behavior isn't just a curiosity, it's rewriting the rules of reality, one photon at a time. On a quiet morning in May 1960, inside a California lab no bigger than a broom closet, physicist Theodore Maiman flicked a switch, and history's first laser beam shot from a ruby rod glowing faintly pink. Journalists dubbed it a solution seeking a problem, but Maiman knew better. He'd just harnessed one of nature's most precise tricks, stimulated emission, where atoms under siege spit out cloned photons in perfect sync. Picture a crowded elevator where one person coughs, suddenly everyone coughs identically, creating a coordinated wave. That's laser light, trillions of photons marching in lockstep, their waves cresting and dipping together like a choreographed dance. This coherence makes lasers the Swiss Army knives of light. Your DVD player reads microscopic pits as laser beams bounce off them, while supermarket scanners decode barcodes the same way. Surgeons wield lasers finer than scalpels to reattach retinas or vaporize tumors without touching healthy tissue. But the real showstopper, LIGO gravitational wave detectors, where laser beams stretch 4 kilometers down vacuum tunnels, sensitive enough to catch ripples from black holes colliding a billion light-years away. When spacetime itself trembles, lasers translate that whisper into something we can measure. Now fast forward to Breakthrough Starshot's audacious dream, tiny probes with sails thinner than soap bubbles, pushed by Earth-based lasers toward Alpha Centauri. The idea, a 1,000-gigawatt laser pulse could accelerate these nanocraft to 20% light speed, reaching our nearest star system in just 20 years. Critics call it sci-fi, but consider this. Lasers already propel microscopic particles in labs, and light sails have successfully orbited Earth. The challenge isn't whether light can push objects, but how to focus that power across interstellar distances without vaporizing the sail. Yet lasers keep defying limits. They've bounced off mirrors left on the moon by Apollo astronauts, measuring Earth's distance down to the millimeter. They cool atoms to near absolute zero, creating bizarre states of matter. They even entangle photons for unhackable quantum communication. From ruby rods to star-hopping beams, lasers prove light isn't just something we see, it's a tool reshaping reality itself, one coherent photon at a time. Deep in the ocean's midnight zone, where sunlight dares not reach, a female anglerfish dangles a glowing lure like a macabre street lamp. This isn't some alien spectacle, it's bioluminescence, nature's oldest light show. The secret, a molecule called luciferin, which reacts with oxygen to cast an eerie blue glow, cooler than a candle flame and far more efficient than any human-made bulb. While Edison's incandescent filaments waste 90% of their energy as heat, fireflies and fungi achieve near-perfect efficiency, turning almost every scrap of chemical energy into pure light. It's as if life cracked the code for the ultimate sustainable lamp millions of years before we even tried. The chemistry behind this is nothing short of elegant. When luciferin meets the enzyme luciferase named after Lucifer, the light bringer, it triggers a reaction that excites molecules to a higher energy state. As they relax, they release photons. No combustion, no wasted heat, just clean, cold light. Scientists call it chemiluminescence, and it powers everything from glowing plankton that paint waves electric blue to railroad worms in the Amazon with green headlights and red taillights. Even mushrooms like the ghostly jack-o'-lantern fungus use it to attract spore-spreading insects, turning the forest floor into a subterranean constellation. This raises a tantalizing question. Could bioluminescence predate photosynthesis? Some researchers think so. In Earth's early days, when the sun's rays barely pierced a toxic atmosphere, primitive microbes might have first evolved light-making genes not to see, but to communicate, or even detoxify oxygen, which was poison to many ancient organisms. Today, that legacy lives on in creatures like the Hawaiian bobtail squid, which farms bioluminescent bacteria in its belly as camouflage. Moonlight filtering through water would cast the squid's shadow, unless its bacterial partners glow to erase it, blending the squid into the seascape like living invisibility cloaks. Now imagine applying nature's blueprints to our cities. Biochemists are already splicing firefly genes into tobacco plants, making leaves that glow softly. Others engineer bacteria to light up in the presence of landmines or toxins. The goal, streetlights replaced by glowing trees or surgical rooms illuminated by harmless microbial lamps. It's not just poetic, it's practical. A single jar of bioluminescent algae can outshine an electric bulb for months with just occasional shaking to recharge its oxygen supply. Which leads us to the cosmos. If life on Earth mastered cold light in crushing depths and toxic jungles, why not elsewhere? Europa's ice-crusted ocean or Enceladus's hydrothermal vents could harbor organisms glowing in eternal darkness. NASA proposed Orbilume mission aims to detect bioluminescent flashes on exoplanets, not with telescopes, but by listening for their unique chemical signatures in alien atmospheres. After all, in a universe where even the laws of physics seem to bend, why wouldn't light, the universe's most versatile language, find infinite ways to speak? Inside every leaf, beneath the waxy surface we barely notice, lies one of evolution's greatest masterpieces, a light-harvesting machine so precise it puts our best solar tech to shame. When sunlight strikes a chloroplast, it doesn't just land on a green blob. It's caught by an intricate antenna system called the photosystem, where pigments like chlorophyll arrange themselves like a microscopic amphitheater tuned to specific light frequencies. But here's where it gets quantum. For decades, scientists assumed energy from absorbed photons hopped randomly between molecules until reaching the reaction center, like a pinball bouncing through obstacles. Then, in 2007, experiments revealed something astonishing. Energy doesn't just hop, it spreads out like a wave, testing all possible paths simultaneously before choosing the most efficient route. This isn't just chemistry, it's quantum coherence, where plants exploit the same wave-particle duality that baffled physicists in labs. Compare this to human-made solar panels, which lose about 70% of captured energy as heat. Silicon cells rely on photons knocking electrons loose, but they can't handle low-energy red light or high-energy ultraviolet efficiently. Meanwhile, a leaf uses nearly every photon, splitting water molecules with precision we've yet to replicate. Evolution's solution, a two-stage process. Photosystem 2 cracks water, releasing oxygen as a byproduct, the very oxygen we breathe, while Photosystem 1 crafts energy-rich molecules. It's a billion-year-old battery, charged by sunlight and fine-tuned across epochs. Now, labs worldwide are racing to mimic this elegance. Artificial photosynthesis aims to capture sunlight and store its energy as hydrogen fuel, bypassing the inefficiencies of combustion. Imagine sheets of smart foil floating on ponds, using sunlight to split water into clean burning hydrogen. No coal, no emissions, just thin films working like synthetic leaves. The challenge, replicating nature's quantum tricks without chloroplasts. Some teams embed light-sensitive molecules in metal organic frameworks. Others engineer bacteria to secrete biofuel when exposed to light. The dream, a world where energy doesn't come from drilling or mining, but from harnessing light the way life always has, with quiet, relentless ingenuity. Yet the most humbling thought isn't just that plants outperform our tech. It's that every blade of grass, every towering oak, is running a quantum process in broad daylight, without cryogenic cooling or vacuum chambers. While we chase quantum computers that work at sub-zero temperatures, nature's been running photosynthesis at room temperature for 3 billion years. Maybe the real mystery isn't how light works, but how life learned to dance with it so flawlessly. In the heart of a nuclear reactor's cooling pool, something impossible happens. A ghostly blue glow pulses through the water, as if the depths have stolen a piece of the sky. This isn't reflected light or some trick of chemistry. It's Cherenkov radiation, one of nature's most vivid paradoxes. Particles outrunning light itself. Not in a vacuum, of course. Nothing breaks Einstein's ultimate speed limit there, but in water, where light slows to a crawl, high-energy electrons can briefly sprint past it, like a jet breaking the sound barrier. The result, a shockwave of photons, an optical sonic boom that paints the water an ethereal blue. The physics behind this glow is as elegant as it is strange. Just as a supersonic plane compresses air into a thunderous cone, a charged particle moving faster than light speed in water creates an electromagnetic wake. The particle polarizes nearby atoms, which then snap back into place, releasing coordinated photons. Because this happens in a cone behind the particle, the light appears focused, almost directional, a luminous fingerprint of something moving unimaginably fast. But Cherenkov's reach extends far beyond reactor pools. Take neutrino detectors like Super Kamiok, and in Japan, a cavernous tank filled with 50,000 tons of ultra-pure water. When the occasional neutrino interacts with a water molecule, it spawns a charged particle that can trigger Cherenkov light. Thousands of photomultiplier tubes lining the tank catch this fleeting glow, allowing scientists to reconstruct the neutrino's energy and direction. It's how we've caught neutrinos from supernova, the sun, even particle beams fired through Earth from accelerators hundreds of miles away. Now scale this up to cosmic proportions. Supermassive black holes like the one at the center of Galaxy M87 fired jets of plasma at nearly light speed. As these particles plow through intergalactic gas, they generate Cherenkov radiation, not invisible light, but across the electromagnetic spectrum, gamma rays, X-rays, radio waves. Telescopes like the Event Horizon Telescope don't just see black holes. They detect the Cherenkov-like signatures of particles spiraling along magnetic fields at relativistic speeds, painting the invisible contours of spacetime itself. Which raises a tantalizing question: could spacetime ever Cherenkov? Some theories suggest that if the fabric of reality has a quantum structure, a sort of pixelation at the Planck scale, then particles might interact with it in unexpected ways. Just as light slows in water, perhaps ultra-high-energy cosmic rays could momentarily outpace light's effective speed in this quantum medium, creating a spacetime shockwave. It's pure speculation for now, but detectors like the Pierre Auger Observatory are hunting for anomalies that might hint at such physics. So the next time you see that eerie reactor glow in documentaries, remember, you're glimpsing a universal phenomenon, one that connects nuclear labs, subterranean neutrino cathedrals, and the jets of distant quasars. Cherenkov radiation isn't just a curiosity. It's light itself bearing witness to the universe's most extreme speeds, a cosmic speedometer written in blue. Staggering across a scorching desert highway, you suddenly spot an oasis shimmering in the distant water, rippling beneath palm trees where none should exist. This cruel mirage isn't just thirst playing tricks, it's light itself bending to the whims of physics. As heat radiates off the asphalt, it creates layers of air at different temperatures, each with its own density. Light speeding through cooler, thicker air up high moves slower than light in the hotter, thinner air near the ground. This speed difference causes light rays to curve upward as they travel, like a car veering when one wheel hits mud. Your brain, assuming light always travels straight, projects the distorted sky light onto the ground, painting illusory pools where only sand exists. Now zoom out to cosmic scales where gravity performs an even grander illusion. When light from distant galaxies passes near massive galaxy clusters, their immense gravity warps spacetime itself, bending light's path like a funhouse mirror. Einstein predicted this gravitational lensing in his theory of relativity, but even he was stunned when astronomers first observed it. Entire galaxies stretched into glowing arcs around foreground clusters. These natural telescopes magnify objects too faint to see otherwise, revealing infant galaxies from the universe's dawn. The eerie parallel, just as desert air gradients create false oases, space-time curvature crafts multiple images of the same quasar, or even smears galaxies into Einstein rings, perfect circles of distorted starlight. Then there's the legendary green flash, a phenomenon wrapped in sailors' lore and scientific wonder. As the sun dips below the horizon, its final sliver can sometimes blaze emerald for mere seconds. This isn't magic, it's Earth's atmosphere acting like a prism. When sunlight skims the horizon, it passes through thicker air, scattering blue and violet light completely while bending green slightly more than red. Under perfect conditions, that differential refraction lets green dominate for a fleeting moment before vanishing. The catch: it's rarer than myths suggest, requiring still air, a flat horizon, and keen timing. Most reported green flashes are actually afterimages from staring at the setting sun too long. What binds these illusions together is light's intimate dance with matter. Whether air molecules, warped spacetime, or ocean humidity, anything light touches alters its path, speed, or color. Modern holograms exploit this by bending light around 3D shapes, while metamaterials engineered surfaces with microscopic structures can redirect light to create invisibility cloaks. Even your eyes deceive you daily. The blue sky is sunlight scattering off nitrogen molecules, and rainbows are water droplets splitting white light into spectral bands. So next time you see a mirage or a lensed galaxy, remember, you're not witnessing light's failures, but its deepest truths. Reality isn't just what light shows us, it's how light negotiates every obstacle, every force, every twist in spacetime's fabric to tell its story. And sometimes the most revealing moments come when that story gets bent. Claude Monet once spent months painting the same haystacks at different times of day, obsessively chasing how dawn's gold dissolved into noon's white glare before softening into violet twilight. His brushstrokes weren't just capturing objects, they were documenting light's restless transformation of the world. Meanwhile, J.M.W. Turner took the opposite approach, throwing caution to the wind with tempestuous seascapes where light didn't illuminate, it exploded. His famous snowstorm steamboat isn't just a ship in peril. It's a vortex of luminescent chaos where sunlight and storm collide in a whirlpool of chrome and charcoal. These two masters reveal light's dual personality. Monet showed its quiet, fleeting subtleties, while Turner painted its raw, untamed power. Fast forward to the 20th century, and artist James Turrell turns the canvas inside out. Instead of painting light, he sculpts with it, using carefully calibrated spaces to trick our brains into seeing solid walls as infinite voids or conjuring illusory cubes from thin air. His Rodin crater, an extinct volcano transformed into a celestial observatory, frames sunlight so precisely that visitors report time itself seeming to slow. Turrell doesn't represent light. He hijacks our perception, proving that what we see is just our brain's shaky interpretation of wavelengths. This dance between light and human experience stretches back millennia. The ancient Egyptians worshipped Ra, a sun god who sailed his golden bark across the sky each day, while the Inti cult of the Incas sacrificed gold metal they called the sweat of the sun to ensure light's return. Even Stonehenge's towering monoliths align with solstice sunrises, stone calendars tracking light's cyclical promise. Today, we've swapped rituals for science but chase the same goal: light's power to heal. Seasonal affective disorder lamps mimic summer's glow to combat winter depression, while blue light-blocking glasses promise deeper sleep by filtering out wavelengths our ancestors never encountered after sunset. Yet the most fascinating twist lies in how art's light metaphors fuel science. Physicists speak of wave-particle duality, like Turner's turbulent brushstrokes, order and chaos intertwined. Quantum entanglement echoes Turrell's perceptual games, where observing one photon instantly changes its distant partner. Even Monet's serial haystacks find a parallel in astronomy's time-lapse images of nebulas, revealing how light chronicles cosmic evolution. The lesson, however we frame it through paint, prayer, or photodiodes, light remains the ultimate storyteller, weaving together perception, belief, and the very fabric of reality. In 1887, inside a basement laboratory at what's now Case Western Reserve University, Albert Michelson and Edward Morley were assembling what looked like a bizarre cross between a jewelry box and a carnival ride. Their contraption, a delicate table floating on a pool of mercury with mirrors and light beams arranged with micrometer precision, was hunting for something no one had ever seen: the luminiferous ether. This invisible medium was supposed to permeate the universe like an endless, intangible ocean, the substrate through which light waves rippled, just as sound needs air to travel. Scientists from Newton to Maxwell had treated its existence as gospel. Even the word ether came from the Greek for upper air, a celestial substance whispered about since antiquity. Michelson, already famous for his exacting measurements of light speed, had devised an ingenious test. If Earth was plowing through this ether as it orbited the Sun, then light beams shot in the direction of Earth's movement should be slightly faster than those sent perpendicular to it, like a swimmer racing downstream verses across a river. Their interferometer, with its mirrored arms, would split a single light beam into two paths at right angles, then reunite them to create interference patterns. Any shift in those patterns would betray the ether's presence. After months of painstaking adjustments, including rebuilding the apparatus on a stone slab to block vibrations from horse carts outside, they finally took measurements at different times of day and year, accounting for Earth's changing velocity. The result: nothing, not a flicker. Light speed refused to budge, no matter which way they aimed it or how fast Earth moved. The scientific world reeled. Michelson called it a failed experiment, but the implications were seismic. Either Earth was somehow stationary at the universe's center, a laughable idea, or the ether didn't exist. For 18 years, physicists floundered, patching theories with increasingly awkward fixes. Then came a 26-year-old patent clerk named Albert Einstein, who saw Michelson and Morley's failure for what it truly was: a clue. If light speed was constant regardless of motion, he reasoned, then time and space themselves must bend to accommodate it. Thus, special relativity was born, rewriting the rules of reality by declaring that the laws of physics hold steady for all observers, no matter how fast they're moving. The ether wasn't just invisible, it was unnecessary. Yet Michelson and Morley's legacy extends beyond relativity. Their experiment whispers a cautionary tale. How often do we mistake our mental models for reality? Before them, the ether seemed as obvious as gravity. Today, we might be equally blind to dark matter's true nature or the quantum vacuum's hidden structure. Their meticulous null result reminds us that sometimes the most profound discoveries come not from finding what you seek, but from the universe's polite, relentless refusal to conform. And that's the beauty of science. It's not about proving we're right, but discovering how gloriously wrong we might be. Hidden inside the humming data centers powering your online life, a quiet revolution is brewing, one where streams of light are beginning to replace the rivers of electrons that have long flowed through silicon chips. This is the dawn of photonics, and it's poised to rewrite the rules of computing. Traditional silicon chips, those tiny marvels of the digital age, are hitting a wall. As transistors shrink to near-atomic scales, electrons bottleneck in copper wires, generating crippling heat and slowing speeds. But photons, they glide through microscopic glass highways without resistance, barely warming their surroundings. Companies like Intel and IBM are now embedding lasers and light guides directly into processors, creating hybrid chips where electrons handle calculations and photons ferry data at the speed of, well, light. The real magic happens when entire chips ditch electrons altogether. Imagine a processor where logic gates flicker with beams instead of currents, where ones and zeros are encoded in light pulses instead of voltage spikes. Optical computing could smash through barriers that choke conventional silicon, solving complex optimization problems in moments. Tasks like simulating protein folds for drug discovery or plotting hyper-efficient global shipping routes. And because photons don't interact with each other the way electrons do, optical chips could perform countless operations simultaneously without interference. It's like replacing a single-lane mountain road with a 1,000-lane superhighway, all running in parallel. This isn't science fiction. Beneath your feet right now, fiber optic cables already form the backbone of the internet, carrying 99% of global data as pulses of light. Each hair-thin strand can transmit hundreds of terabits per second, enough to stream every movie ever made in minutes. But the next leap comes when we bring that speed from underground cables onto our desks. Startups like Light Matter are building photonic AI accelerators that outperform traditional chips by orders of magnitude, using light to turbocharge machine learning. Picture training a facial recognition system not over weeks, but coffee breaks. Now, crank the concept to 11 with quantum photonics. While classical optical computing uses light as a faster electron substitute, quantum photonics exploits light's inherent weirdness, its ability to exist in multiple states at once. Photons can entangle across vast distances, their properties mysteriously linked even when separated by galaxies. Quantum computers using these photons could crack encryption, model exotic materials, or simulate entire universes in ways no silicon machine ever could. Labs from China to California are racing to build them, trapping photons in chips cooled near absolute zero, or bouncing them between ultra-reflective mirrors in vacuum chambers. The irony, we're circling back to light's earliest role in technology, not as illumination, but as information. Just as ancient signal fires relayed messages across mountaintops, tomorrow's photonic chips might use light to whisper secrets between quantum bits or beam calculations through the fabric of spacetime itself. The future isn't just bright, it's luminous. For most of human history, stepping outside at night meant being swallowed by an ocean of stars. Ancient Egyptians charted their calendars by Sirius's rising. Polynesian navigators crossed thousands of miles guided by the Southern Cross, and Greek poets wove constellations into mythology. Today, stepping onto a city balcony often reveals just a handful of the brightest stars, the rest drowned in an electric tide. The Milky Way, once a universal spectacle, is now invisible to 1/3 of humanity. This isn't just about lost beauty, it's a fundamental rewiring of our relationship with the cosmos, with consequences rippling through ecosystems and cultures alike. Take loggerhead sea turtles, whose hatchlings have followed moonlight reflections on the ocean for millions of years. Now, beachfront developments disorient them with artificial glow, sending countless babies crawling inland toward highways and predators instead of the sea. Or consider migratory birds like indigo buntings, which navigate by starlight. Skyscraper windows and floodlit towers lure them into fatal collisions, contributing to nearly 1 billion bird deaths annually in North America alone. Even trees get tricked. Some urban species, bathed in perpetual streetlight, delay shedding autumn leaves until frost kills them. The night's natural rhythms, honed over eons, are unraveling under a blanket of misdirected photons. Yet the loss cuts deeper than ecology. entire cosmologies are fading. The Tohono O'odham people of the Sonoran Desert traditionally used the stars to mark seasonal rains for planting. In New Zealand, Maori sailors still teach celestial wayfinding, but must venture far from cities to find intact skies. Even Western astronomy suffers. Observatories like Mount Wilson, where Edwin Hubble proved galaxies exist beyond our own, now battle Los Angeles' light dome, which outshines all but the brightest celestial objects. The fightback has begun in places like Namibia's Namib Rand Nature Reserve, where night skies are legally protected as natural heritage. Visitors there witness the Magellanic Clouds so vivid they cast shadows, a sight Galileo would recognize. Similar dark sky reserves span from Chile's Atacama Desert to England's Yorkshire Dales, combining low-impact lighting with education. The solutions aren't complicated. Shielded streetlights that direct beams downward, motion sensors that activate only when needed, and warmer LED hues that minimize blue light's disruptive glare. Some cities like Flagstaff, Arizona, have adopted these measures and seen energy bills drop while stargazing tourism booms. Perhaps the most poetic fix comes from fireflies. These beetles, whose courtship flashes are being masked by artificial light, might hold a clue. Their bioluminescence is nearly 100% efficient. No wasted energy, no disruptive spill. As we relearn how to light our world without extinguishing the night's magic, their gentle glow reminds us brilliance doesn't have to mean blindness. In December 1995, astronomers made a bet that would redefine our place in the cosmos. They pointed the Hubble Space Telescope at a patch of sky no bigger than a grain of sand held at arm's length, a region near the Big Dipper so empty that ground-based telescopes saw nothing but black. For 10 straight days, Hubble's fragile mirrors collected photons that had traveled across eons, gambling valuable observation time on what might have been a celestial desert. When the images came back, the scientific world gasped. That empty spot contained over 3,000 galaxies, each a swirling island of billions of stars, crammed into a slice of sky you could cover with a pinhead. The Hubble Deep Field wasn't just a photograph, it was a core sample of the universe, drilling through layers of cosmic time. The faintest smudges in that image were galaxies so distant their light had been traveling for over 13 billion years, meaning we were seeing them as they existed when the universe was less than 5% of its current age. Imagine catching a glimpse of your hometown as it appeared in the 1800s, except this was the universe in its infancy, galaxies still clumping together like toddlers holding hands. Some showed bizarre shapes, train wrecks of spinning gas where gravity hadn't yet sculpted elegant spirals or smooth ellipticals. This was cosmic archaeology with light itself as the time machine. Now leap forward to the James Webb Space Telescope, Hubble's infrared successor. Where Hubble saw toddlers, Webb peers into the cosmic nursery. Its first deep-field image revealed galaxies from just 300 million years after the Big Bang, so ancient their stars had barely begun cooking heavy elements. The light from these objects is stretched so severely by the expanding universe that it arrives as faint infrared whispers, like hearing a song played on a tape that's been slowed until the melody warps. Webb's mirrors, chilled to near absolute zero, catch these dying embers from the universe's first dawn. Here's the staggering implication. Every photon reaching our telescopes carries layered histories. The light from a 12 billion-year-old quasar might have passed through interstellar dust clouds, been bent by a galaxy cluster's gravity, and finally been captured by a silicon sensor, all while carrying chemical fingerprints from the early universe's pristine gas. It's as if starlight is cosmic Morse code, with each wavelength, each deflection, and each delay encoding another chapter of the universe's story. The question isn't just how far we can see, but how much of the past we can learn to read in these ancient beams. Richard Feynman once called quantum electrodynamics the strange theory of light and matter, and for good reason. Picture two electrons repelling each other not because of some invisible force field, but because they're constantly hurling invisible photons back and forth like frenzied messengers. These aren't ordinary photons you could catch with a detector. They're virtual particles, fleeting violations of energy conservation allowed by quantum uncertainty. Feynman captured these wild interactions in his iconic diagrams, stick figure cartoons where straight lines represent electrons, squiggles are photons, and every intersection tells a story of collision or exchange. What looks like a simple sketch is actually a mathematical powerhouse, turning what would be nightmare calculus into visual poetry. The brilliance of QED lies in its absurd precision. Take an electron's magnetic moment, a measure of how it behaves like a tiny compass needle in a magnetic field. QED predicts this value to 12 decimal places, matching experiments with an accuracy equivalent to measuring the distance from New York to Los Angeles within the width of a human hair. Each decimal requires calculating thousands of possible particle interactions, electrons emitting and reabsorbing virtual photons, those photons briefly morphing into electron-positron pairs, and even ghostly loops where particles pop in and out of existence. The more intricate the Feynman diagram, the tinier its contribution, but ignore enough loops, and your calculations drift from reality. Yet for all its success, QED leaves tantalizing gaps. Why do photons, unlike every other fundamental particle, seem completely massless? Experiments show if they have any mass at all, it's less than a trillionth of an electron's, but zero is a tough pill to swallow in physics. Some theories suggest photons might gain vanishingly small masses in hidden dimensions or extreme cosmic conditions. Then there's the vacuum catastrophe. QED predicts empty space should seethe with infinite energy from virtual particles, yet the observed cosmological constant is eerily quiet. It's as if the universe keeps double entry books, with most quantum transactions mysteriously cancelling out. Feynman's doodles ultimately reveal a cosmos where light isn't just illumination, it's the glue holding reality together. Every magnet's pull, every chemical bond, every shimmer of sunlight stems from this ceaseless photon exchange. The catch: we're still decoding the fine print in light's quantum contract with matter. Ancient Egyptians watched the sun's daily rebirth with such reverence they built an entire cosmology around it. To them, the sun god Ra didn't just rise, he embarked on a perilous journey. Each night, he boarded his golden bark to navigate the underworld's 12-hour darkness, battling the serpent Apophis who sought to swallow the sun whole. His victory at dawn wasn't just celestial mechanics. It was a divine promise that light would always prevail over chaos. Meanwhile, across the Mediterranean, Greek poets envisioned Helios driving a fiery chariot across the sky, his four-winged horses scattering stars in their wake. The imagery diverged, a boat versus a chariot, but the underlying awe was identical. Light as both life-giver and cosmic conqueror. Half a world away, the Diné Navajo people revered the holy wind not just as air, but as an invisible, luminous force threading through all living things. This sacred breath carried light's essence, connecting humans to the land and sky in a web of radiant energy. Where Egyptian and Greek myths personified light as gods, Navajo tradition saw it as something more intimate, the spark animating every heartbeat, the glow within each thought. Yet all three cultures shared a profound understanding: light wasn't merely physical. It was the universe's vital pulse. Fast forward to today, and we've swapped chariots for photons, but the metaphors remain startlingly similar. We speak of enlightenment as if wisdom were a kind of inner dawn, or describe genius as brilliance, linguistic relics of our ancestral awe. Modern physics even echoes these ancient intuitions. Quantum fields humming with potential energy aren't so different from the Navajo's luminous holy wind, and Ra's nightly battles mirror our scientific understanding of entropy's constant tug of war with order. What binds these threads across millennia isn't just curiosity, it's recognition. Whether carved into temple walls or coded into equations, humanity's relationship with light transcends culture and epoch. We've always sensed, even before we could prove, that light is more than what meets the eye. It's the universe's oldest language, and we're still learning to speak it. In 1841, a Parisian inventor named Jacques Babinet demonstrated something that seemed more like magic than science, bending light around corners using nothing but a curved stream of water. His light pipes were little more than novelty tricks at the time, but they planted the seed for an idea that would revolutionize communication. Fast forward to the 1950s, when British physicist Harold Hopkins bundled thousands of glass fibers together, proving light could carry images through twisted strands. Doctors pounced on the invention for endoscopes, peering inside the human body without surgery. But the real breakthrough came in 1966, when Charles Cow calculated that ultra-pure glass fibers could transmit light for kilometers with minimal loss. His discovery earned a Nobel Prize and birthed the backbone of our digital age. Today's fiber optic cables are marvels of precision, strands of glass so pure that if seawater were this clear, you could see the ocean floor from space. Each hair-thin fiber guides light via total internal reflection, the optical equivalent of a bobsled track. When light hits the glass wall at a shallow angle, it ricochets perfectly rather than escaping, zigzagging down the fiber at nearly light speed. The trick, a core of ultra-clear glass wrapped in a cladding layer with a slightly lower refractive index, creating a mirrored corridor for photons. Modern fibers carry terabits per second, enough to broadcast every episode of every Netflix show simultaneously through a tube thinner than spaghetti. The race to wire the planet reached its climax in 1988 with the first transatlantic fiber optic cable, TAT-8. Earlier copper cables carried mere hundreds of calls. TAT-8 could handle 40,000 simultaneous conversations as pulses of light. Laying it required ships carefully unspooling 2,000 miles of armored cable across the ocean floor, avoiding undersea cliffs and volcanic vents. Today, over 400 such cables crisscross the seabed, forming a global nervous system that transmits 99% of international data, every tweet, stock trade, and video call flowing as flickers of light beneath the waves. Now peer into the future where photonics could escape Earth entirely. NASA's lunar laser communication demonstration beamed data from the Moon to Earth at 622 megabits per second, 6 times faster than radio. Imagine a solar system-wide internet, with laser relays between Mars bases and asteroid mining outposts streaming 4K telemetry in real time. Closer to home, quantum fiber networks could use entangled photons to create unhackable links where any eavesdropping would instantly alert the system. Researchers are even toying with photonic highways in space satellite constellations, routing data via laser crosslinks, bypassing terrestrial bottlenecks entirely. From Victorian parlor tricks to interplanetary broadband, light's journey through glass has become the silent pulse of civilization. And as we stand on the brink of photonic revolutions, from quantum internet to space lasers, one thing's certain: the future doesn't just run on light. It rides it. Imagine two identical twins, each holding a strange clock, not with gears or digits, but with light. These light clocks work by bouncing a single photon between two mirrors. Every time the photon completes a round trip, the clock ticks, Simple, right? Now picture twin A staying on Earth while twin B blasts off in a rocket approaching light speed. Here's where Einstein's universe throws us a curveball. From Earth's perspective, twin B's light clock appears to slow down because the photon isn't just moving up and down, it's also racing sideways with the spacecraft. The photon now traces a long, diagonal path between mirrors, making each tick take longer. Time itself stretches for the traveling twin. When twin B returns, decades might have passed on Earth while only years elapsed on the ship. The so-called paradox, it's not really a paradox at all, just relativity in action. The key lies in asymmetry. Unlike classic thought experiments where motion is relative, twin B's journey involves acceleration, speeding up, turning around, and decelerating. These forces break the symmetry between the twins, making their experiences fundamentally different. General relativity steps in here, revealing how acceleration warps spacetime in ways that pure velocity doesn't. Twin B doesn't just feel time differently. Their path through the cosmos literally bends the fabric of reality, leaving them younger than their Earth-bound sibling. This isn't just theoretical sleight of hand. GPS satellites orbiting Earth experience time dilation too, though on a minuscule scale. Moving at 14,000 kilometers per hour, their clocks tick about 7 microseconds slower each day due to special relativity. But because they're also farther from Earth's gravity, general relativity speeds them up by 45 microseconds daily. Net result, without correcting for this 38 microsecond daily drift, GPS locations would accumulate errors of kilometers within hours. Your phone's navigation literally depends on Einstein's twin thought experiment playing out in real time, with atomic clocks high above Earth constantly adjusting to the dance between motion and gravity. So the next time you glance at a clock, whether it's light-powered or atomic, remember, time isn't a universal metronome. It's a fluid, personal experience shaped by speed, gravity, and the very structure of the cosmos. And somewhere in the heavens, a fleet of satellites is quietly proving it, one corrected nanosecond at a time. On June 10, 2010, high above Earth's atmosphere, a Japanese spacecraft named Icaros did something no machine had ever attempted. It unfurled a sail thinner than a human hair, stretching 14 meters across, and let sunlight itself become its engine. Unlike traditional rockets that burn fuel, Icaros relied on pure physics, photons streaming from the sun, each carrying a tiny kick of momentum. When these particles of light struck the sail's reflective surface, they bounced off like microscopic ping-pong balls, transferring their energy and gently nudging the spacecraft forward. No explosions, no exhaust, just the silent, relentless push of sunlight. Over 6 months, this pressure built up, accelerating Icaros enough to cross Venus's orbit, proving that sailing on light wasn't science fiction anymore. Here's the wild part. Photons might be massless, but they still pack momentum, a quirk of quantum mechanics where energy and motion intertwine. Think of a flashlight beam. You can't feel it, but if you were floating in space with a sail the size of a city block, those imperceptible shoves from trillions of photons would add up. Newton's third law applies even to light. Every action has an equal and opposite reaction. The push is minuscule, about the weight of a paperclip resting on your palm per square kilometer of sail. But in the frictionless void of space, constant acceleration can eventually reach breathtaking speeds. Enter Breakthrough Starshot, an audacious plan to harness this principle for interstellar travel. The vision, a fleet of gram-scale probes, each with a sail no larger than a bedsheet, propelled by a 100-gigawatt laser array on Earth. The laser blast, lasting minutes but packing the punch of a nuclear reactor, would accelerate these nanocraft to 20% light speed, fast enough to reach Alpha Centauri, our nearest star system, in just 20 years. The challenges are staggering, keeping the sail from vaporizing under the laser's fury, steering a target smaller than a postage stamp across light years, and detecting signals weaker than a whisper from probes that'll coast past their destination at breakneck speed. Yet if it works, humanity could get close-up data from another star within our lifetime. Could light alone really carry us to the stars? For robotic scouts, perhaps, but human crews face harder limits. The problem isn't just speed, it's stopping. A sail pushed by Earth-based lasers has no brakes at the other end, and even if it did, hauling a starship's mass would require lasers of unimaginable scale. Some theorists dream of beam riders, sails catching light from stationary lasers, or even tapping the pressure of starlight itself for slower, generational voyages. Others imagine sails made of metamaterials that change reflectivity mid-flight, allowing steering without fuel. The poetry of light sails lies in their simplicity. They turn the universe's oldest force into an engine, riding the same beams that warmed Earth's first microbes. Whether they'll carry our descendants to Alpha Centauri or remain celestial curiosities, one thing's certain: after millennia of staring at the stars, we've learned to sail on their light. Picture a firefly blinking on a summer night. Its glow erupts and vanishes in an instant like a tiny lightning strike. Now reach for that glow in the dark star stuck to your childhood bedroom ceiling. Charge it with sunlight and it'll emit a faint, persistent radiance for hours. Both phenomena involve light emission, but the mechanics couldn't be more different. Fireflies use fluorescence, a rapid process where electrons absorb energy and immediately release it as visible light. The glow-in-the-dark toy relies on phosphorescence, where those excited electrons get trapped in a higher energy state, trickling back down slowly like sand through an hourglass. The secret lies in quantum mechanics rulebook. When a molecule absorbs energy, whether from sunlight, UV light, or a chemical reaction, its electrons leap to higher orbits like balls tossed onto a staircase. In fluorescence, they bounce right back down, releasing their energy as photons almost instantly. But phosphorescent materials have a clever trick. Their electrons get snagged in forbidden energy levels due to quantum spin states, delaying their return. This creates that signature afterglow, sometimes lasting minutes or even hours. Scientists tweak these delays by doping crystals with rare earth metals: europium for red glow, strontium illuminate for eerie green, engineering persistence like cosmic dimmer switches. Now grab a UV flashlight and step into a detective's shoes. Shine it on a scorpion, and the creature's exoskeleton erupts in an eerie blue-green blaze. This isn't a party trick, it's fluorescence revealing nature's hidden signatures. Scorpion cuticles contain beta-carbolines, molecules that absorb UV and re-emit visible light, possibly helping them detect moonlight or avoid sun damage. Police use the same principle to spot counterfeit bills. Real currency paper lacks optical brighteners, so under UV light, fake notes often glow brighter than genuine ones, their fibers screaming under ultraviolet scrutiny. But the real magic happens beneath the waves. Dive into a coral reef at dusk with a blue dive light, and suddenly, the reef transforms into a neon dreamscape. Brain corals pulse green, sea anemones flash orange, and even plankton leave glowing trails. This is biofluorescence, where organisms absorb blue light and spit it back out at lower energies, painting the ocean in living lasers. Some fish see this glow naturally, using it like a secret visual language. Scientists suspect fluorescence might help corals sunscreen their symbiotic algae or even communicate. It's a reminder that light's most dazzling performances often happen where human eyes rarely wander. By the late 19th century, physicists faced a puzzle so stubborn it threatened to unravel their understanding of light itself. Picture a blacksmith's forge. As the metal heats, it glows dull red, then orange, then white hot. Classical physics insisted this color shift should follow predictable rules like a musical scale where higher temperatures simply meant higher frequencies. But when scientists measured the exact spectrum of light emitted by heated objects, the numbers refused to cooperate. The equations predicted an impossible, ultraviolet catastrophe, where hotter objects would emit infinite energy at shorter wavelengths. Not only was this clearly wrong, it hinted at something deeply flawed in their theories. Enter Max Planck, a reluctant revolutionary. In 1900, after years of wrestling with the math, he made a desperate gamble. What if energy wasn't a smooth, continuous flow like water from a tap, but came in tiny, indivisible packets? He called these chunks quanta, imagining light as a series of abrupt jumps rather than a steady wave. To his shock, the numbers aligned perfectly. His formula matched experimental data with eerie precision, but at a cost. It shattered the elegant continuity of classical physics. Planck himself didn't believe his idea reflected reality. He saw it as a mathematical trick, a temporary fix. Yet this trick became the foundation of quantum mechanics. The irony was exquisite. Classical physics, so successful at predicting planetary orbits and electromagnetic waves, crumbled when faced with something as ordinary as a glowing stove. Meanwhile, Planck's quantum hypothesis, born from frustration, unlocked the door to the subatomic world. The key difference: classical thinking treated energy like an unbroken line, while quantum mechanics revealed its granular, pixelated nature. It's like comparing a flowing river to a stream of individual water droplets. Both describe movement, but on fundamentally different scales. Today, Planck's breakthrough echoes across cosmology. The cosmic microwave background, the faint afterglow of the Big Bang, reveals a near-perfect blackbody spectrum. It wrinkles and dips a snapshot of the infant universe. Just as heated metals glow exposed quantum quirks, this primordial light carries secrets about spacetime's structure. Modern telescopes like the Planck satellite map these ancient photons with Planck's equations as their guide, proving once again that light, in all its forms, remains the universe's most candid storyteller. On a quiet night in August 2016, orbiting 500 kilometers above China's deserts, a small satellite named Michelson performed an experiment straight out of science fiction. It fired a laser beam toward Earth, but this wasn't ordinary light. It carried pairs of photons so deeply entangled that measuring one instantly determined the state of its twin, no matter the distance between them. The result: the world's first unhackable quantum encrypted video call, bridging Beijing to Vienna with a security protocol written into the fabric of reality itself. This wasn't just a technological leap, it was a glimpse into a future where light's spookiest quantum behavior becomes the backbone of global communication. The magic lies in entanglement, that eerie bond Einstein famously dismissed as spooky action at a distance. When two photons become entangled, they share a single quantum state. Change one, say, by measuring its polarization, and the other snaps into a correlated state instantaneously, even if it's light years away. Michelson exploited this by beaming entangled photons to ground stations separated by over 1,200 kilometers. Any attempt to eavesdrop would disturb the photon's delicate quantum states, alerting users to the intrusion. It's like sealing a letter with wax that shatters if touched, except here, the wax is woven from the uncertainty principle itself. Heisenberg's famous rule that measuring a quantum system inevitably alters it becomes the ultimate security guard. Traditional encryption relies on math problems so complex they'd take centuries to solve, but quantum keys need no such complexity. The mere act of intercepting a quantum signal collapses its state, leaving behind digital breadcrumbs. China's satellite network has already demonstrated quantum-secured banking transactions and government communications, with plans to expand into a constellation covering the entire planet. Now imagine scaling this up to a quantum internet, where entanglement links every device in a global web. Data wouldn't just be encrypted, it would exist in multiple places at once until measured, making hacking physically impossible. Researchers in the Netherlands are already testing quantum repeaters to extend entanglement across cities, while underground fiber networks in Chicago and China shuttle entangled photons between labs. The goal, a hybrid network where classical internet handles everyday traffic, while quantum channels secure everything from elections to nuclear launch codes. What's poetic is how this revolution circles back to light's dual nature, the same wave-particle duality that baffled Newton and Einstein now powers technologies they couldn't have dreamed of. Photons, once mere messengers, have become both lock and key in a new era of communication, proving once again that light doesn't just illuminate our world, it redefines what's possible. Roger Penrose, the Nobel Prize-winning physicist, once proposed an idea so radical it made mainstream neuroscience shudder. What if our brains aren't just biological computers but quantum light processors? At the heart of his theory, co-developed with anesthesiologist Stuart Hameroff, lies a microscopic structure called microtubules. These tiny protein tubes form the skeleton of neurons, and Penrose suggests they might be doing something far stranger than just providing structural support. Inside these hollow filaments, he imagines delicate quantum states forming and collapsing, with photons playing a key role in orchestrating consciousness itself. It's a wild claim that the flicker of quantum light inside our cells could be the spark of awareness, the thing that transforms electrical noise into the symphony of subjective experience. Mainstream neuroscience, of course, remains deeply skeptical. Most researchers see consciousness as an emergent property of neural networks, billions of neurons firing in complex patterns, with no need for quantum weirdness. After all, the warm, wet environment of the brain seems like the worst possible place for fragile quantum states to survive. Decoherence, the tendency for quantum systems to collapse when disturbed, should wreck any delicate quantum computations almost instantly. Yet Penrose counters with a fascinating twist. Microtubules might be shielded enough to preserve quantum coherence, with light acting as a kind of quantum messenger between neurons. It's a fringe idea, but one that refuses to die partly because no one has fully explained how sheer complexity alone gives rise to the vivid, unified experience of being you. Here's where the philosophy kicks in. If Penrose is even fractionally correct, then light isn't just something we perceive, it might be woven into the very fabric of perception itself. Think about it, every color, every shadow, every sunset you've ever seen is your brain's interpretation of electromagnetic waves. But what if that interpretation isn't passive? What if the act of observation of light interacting with the quantum processes in your brain actually shapes reality in some small but profound way? It's an echo of the old philosophical question, does the moon exist if no one is looking at it? Quantum physics already suggests that particles don't have definite states until measured. Could consciousness, fueled by light's quantum dance, be the ultimate measuring device? Of course, this veers into deep metaphysical waters. Some philosophers argue that equating quantum processes with consciousness is a category error, like saying a computer understands poetry because it can rearrange words. Others, inspired by Eastern philosophies, see Penrose's ideas as a bridge between science and ancient intuitions about light as the essence of awareness. The Upanishads, for instance, describe consciousness as self-luminous, needing no external light to reveal itself. Is that just poetic metaphor, or could there be a kernel of truth waiting for science to catch up? For now, the debate rages on, but whether Penrose's theory holds up or not, it forces us to confront a humbling possibility. That light, in all its forms, might be more than just a tool for vision. It could be a silent partner in the mystery of consciousness itself, the unseen thread connecting the quantum world, the biology of our brains, and the rich inner universe of thought and feeling. And that's a glow no microscope can yet fully illuminate. In the late 1990s, a theoretical physicist named Gerard T. Hooft dropped a bombshell that still rattles the foundations of physics today. What if everything we perceive as reality, from swirling galaxies to the neurons firing in your brain, is nothing more than an elaborate illusion? Not a simulation in the digital sense, but a cosmic hologram where the true source code of the universe is written in flickering bits of information on a distant, two-dimensional surface. This is the holographic principle, and it suggests that light itself might be the universe's original programming language, projecting our three-dimensional experience from a hidden, lower-dimensional canvas. The idea sprouted from an unlikely place, the study of black holes. When matter vanishes beyond an event horizon, it seems to erase information from our universe, violating quantum mechanics' sacred rule that information can never be destroyed. But in the 1970s, Jacob Bekenstein and Stephen Hawking discovered something startling. Black holes aren't just cosmic vacuums, they have entropy, a measure of hidden information proportional to their surface area. This hinted that all the data describing what fell inside might somehow be encoded on the black hole's boundary, like a celestial DVD storing a 3D movie on its 2D surface. Fast forward to T. Hooft and Leonard Suskind's work, and the implication became staggering. If black holes can holographically encode information, why not the entire universe? String theory, that labyrinthine framework attempting to unify all forces of nature, gave the holographic principle mathematical teeth. In one of its most concrete realizations, the AD/CFT correspondence, physicists proved that a hypothetical universe with negative curvature, like an infinite funhouse mirror, could be perfectly described by a quantum theory operating on its boundary. Swap hypothetical for our universe, and the implications are dizzying. Every particle collision, every supernova, every thought you've ever had could be shadows cast by quantum light code vibrating on the edge of reality. Lab experiments are now chasing this wild idea. At the University of Amsterdam, researchers cooled 10,000 rubidium atoms to near absolute zero, creating a quantum state where the atoms behaved like a holographic projection of a theoretical, lower-dimensional system. Meanwhile, Fermilab's holometer experiment hunted for telltale pixelation in space-time itself, evidence that reality has a fundamental resolution limit, just like a hologram's graininess when you zoom in too close. So far, no smoking gun, but the quest continues. Here's the mind bender. If the holographic principle holds, light isn't just a feature of the universe, it might be its foundational syntax. Photons crisscrossing the cosmic boundary could be the universe's way of rendering reality in real time, like a graphics card projecting a video game. It's a vision that echoes ancient philosophies, the Hindu concept of Maya, the illusion of material existence, or Plato's allegory of shadows dancing on a cave wall. Except now, the wall might be the edge of the cosmos, and the shadows are you, me, and everything we've ever known. From the moment early humans first huddled around a flickering fire to the quantum labs where entangled photons whisper secrets across continents, light has been our constant companion and greatest teacher. It began as a divine mystery, Ra's golden bark sailing through darkness, Prometheus' stolen flame. but became the lens through which we've decoded the cosmos. We've chased its speed through Jupiter's moons, split it into rainbows with prisms, and trapped it in glass threads thinner than spider silk. Yet for all our progress, light remains delightfully defiant, both particle and wave, tangible and ephemeral, obeying rules that still bend even the sharpest minds. What's astonishing isn't just what light has revealed: black holes warping space-time, DNA's double helix, the afterglow of creation itself, but how it reshapes our very existence. Your smartphone's screen, your city's fiber optic internet, even the GPS guiding your pizza delivery all hum with photons harnessed by quantum wit. Light heals too. Lasers mend retinas, blue wavelengths regulate our sleep, and bioluminescent molecules tag cancer cells like celestial breadcrumbs. Once a tool to banish shadows, it's now the scalpel, the messenger, the artist of our age. And here's the cosmic punchline: you're made of this stuff. Carl Sagan wasn't being poetic when he said, "We are star stuff." Every atom in your hands, your breath, your beating heart was forged in stellar furnaces where light fused hydrogen into carbon, oxygen into iron. The gold in your jewelry, that's stardust too, likely born in a neutron star collision so violent it rippled spacetime. When you stand under the night sky, you're not just observing light, you're meeting the very elements that birthed you, returning home as radio waves and starlight. So tonight, step outside, look up, let your eyes adjust to the glow of stars that died before Earth formed, photons that spent millennia racing toward this moment. Wonder at the questions still unanswered. What's dark matter's hidden hand? How does consciousness flicker to life? Could entangled photons one day link worlds? The adventure's far from over, it's just brightening. If this journey through light's wonders sparked your curiosity, pass the torch. Share this video, because understanding light isn't just science, it's remembering we're all citizens of an radiant, whispering universe. Now go catch some starlight. It's been waiting for you.